Welcome to our class today as we continue with our study of using Noir. So we'll be writing our zero knowledge proofs in Noir as we've been doing. Now, today we just want to look at more other applications. I've called them advanced applications. There are so many applications we can have in zero knowledge proofs. So we cannot exhaust all of them, but we'll be learning one after another. Every other time we learn a new one. Our goal for today's lesson is to understand how to use Noir programming language to build practical zero knowledge circuits. That's what we've been doing, but want to just advance. So we will explore two key applications of zero proofs. One, we've already looked at this, but we shall again be looking at it in details. Set membership proofs. This can be, once we write a circuit, we can apply it in so many other scenarios, but we just want to this time apply here set membership proofs, proving a secret value belongs to a given set without revealing the value itself. That's what we want to do. For example, you may want to prove that, for instance, your country is one of those listed in some other list of countries which qualified for something. So you want to prove that your country is one of them, that you don't want to actually reveal your country. That is just an example. We'll also be applying this knowledge in graph 3 coloring. So we'll be proving to know valid coloring of a graph without revealing the coloring itself. So this can be applied in cases where you want even to schedule something. You want to prove that you know some schedule without revealing the schedule itself. So that is one area we can apply the graph coloring problem. So the other thing, the other goal today is to learn general ZK concepts. See Noir code, we shall be coding in Noir today, and understand real world applications. So that is part of what we'll be doing today. Now, I've just noted here that Noir simplifies writing, testing, and deploying ZK circuits to privacy-preserving proofs. And we've been seeing this, how it simplifies. And again, we continue to see it. Noir simplifies all these things, simplifies the writing. Where you write your codes, it simplifies, makes it easier, simplifies testing, deploying ZK circuits for privacy-preserving proofs. Now, so let's begin with Noir circuit for membership proofs. So we, of course, we will write a circuit and then a zero knowledge proof, and see how to write that and how to verify the proof and so on, how to generate the proof and so on. So today's lesson is how to use Noir circuits to prove in zero knowledge that a private value like a country code is a member of a set. I had already mentioned this. You want to prove that a country, given country, is a member of a given set, is on the list, a given list, and you want to reveal the country, the code of the country, or even the list. So the key concepts and inputs, one, we will prove, you will prove that you know a secret such as a country code without revealing. That is zero knowledge. That is zero knowledge. That means the verifier gains no knowledge other than the fact that you know what the code is. So that is the only thing the verifier would get to know at the end of the proof. Cannot know what the code is. We'll also try to check if the secret input matches any element in the given set. So that is how we will then be checking that your secret input, does it match any element in that set? So what will be our inputs now? Our inputs will be the secret country, that is the hidden code of the country. That will be private. We also have set 0 to set 4, the set of the country code. So you have countries and their codes, we've numbered them set 0 to set 4. But we do not want, of course, your country could be one of these, or it might not be one of these. So when we are writing that circuit, it could be one of these or not. But we will have a set of four countries, 4 codes, and those will be our inputs. And the other input will be the private input, which is a code of the country that you want to prove you know it's part of the set. Now, so what the code will be doing, it'll be comparing the secret code that you enter to each of the other elements of the set. We've had elements of the set from 0 to 4, and you have your secret input. So this is secret input to be compared to set 0, set 1, set 2, set 3, and see whether it matches any of them. So if it asserts any of them, then it means your code is one of the elements in that set. If it doesn't, then it's not. Now, so we'll be doing summation again, and we will assert that the sum is at least 1, i.e. at least 1 match. So that is when you sum and you get 1, then there is a match. It means at least 1 match. Because you can get a sum of 2, you can get a sum of 3, you can get a sum of 4. So that means there's a match. But if the sum is 0, then it means that your code does not match any of that. Means that your country is not a member of the set. So for instance, if your secret code is 42, and the other elements of the set are 1, 2, 42, 4, and 5, and then what the code will be doing will be matching, will be comparing this 42 to members, and see whether it matches any of them. And you can see that 42 does not match with 1, it doesn't match with 2, but it matches with the 42. So that means this proof succeeds because 42 is present in the set. So it matches with the elements of the set. Now, but I talked of some summation. So let's just see how will it be summing. So when they don't match, it's 0, and they don't match again, it's 0. If they match, the result is 1. If they don't, there is a 0, and they don't is 0. So the sum here is 1. So if the sum is 1, it means 42 matches, that there is at least 1 match. There is a 1 match. In fact, not at least 1 match, but there's 1 match. That is why the sum is 1. So I said the sum could even be 2. The sum could even be 3. That if it's 2, it means we have 42 2 times. If it's 3, it means 42 are present 3 times. So there were 3 matches. Now, so that is how we'll be looking at it, but now the code is here. The code is here, and of course you can just write this code and then try to run it. It will just run. I've already written it, and I'll try to run it and see that it runs. Now, these are our inputs. These are our inputs, and we have, they're all fields. And of course, you have your private one. So these others will be public. But because this is the one we want to hide, so you can see secret country field, and we've not indicated whether it's public. If it will be public, we would indicate it that way. But we've also kept these others secret. Also kept them secret so that the verifier does not get to know what they are. Okay, so this is the code. You can just copy and paste in your main.nr. The assertion is here. We assert that the sum is not equal to 0. And so if that is the case, if the sum is not equal to 0, then it means the proof succeeds. That means there is at least one match. But if the sum is 0, then the proof does not succeed because there's no match. Okay, so these are the tests. Want to test. This one will, as I said, you just check whether they match, check whether 42 matches, and it matches once. So if we were to do the sum, this would be 0 plus 0 plus 1 plus 0 plus 0, and the sum is 1, which means the proof, your test has passed. In other words, it means that the given code is one of those in the list because it has matched one code in the list. So it's one of those in the list. And that is what we are looking at. Now let's look at this other set, and our private value this time is 99. And you can see if there's a match, it matches that, it matches that, it does not match, it does not match. So if you were to do summation, every time it matches, gives us 1, matches again gives us 1, then it does not, and this sum is 2. So when the sum is 1, or the sum is 2, or the sum is 3, and so on, it means that the test has passed. In other words, your secret value matched values, matched some other values. So in this case, there were 2 matches. So when there are 2 matches, it means you are, of course, your code you claim to be part of the set is indeed part of the set. Okay, let's see. Let's try this. This time, our secret value is 77, and it's not matching any of the values here. It's not matching any of the values here. So when it does not match, we have zeros, and the sum will be 0. So that means the test fails. This test must fail. In other words, your secret code is not matching any code. So of course, is not among the members of the set. Is not among the members of the set. Now, so let's look at applications of this. The applications of this one is in a white list, e.g., you may want to prove that your country is among the allowed countries or regions. That is one of the things we may want to apply this set membership circuit to. Or even voting systems, you may want to prove that a vote is for a valid candidate. The vote is for a valid candidate, you may want to prove that. Or any situation where private value must be shown to be in the approved set without revealing the value itself. So any scenario where we have such a case where you want to prove that a given value is part of the values given, is part of the set without revealing the members of the set, then you can always apply this apply this circuit. So it's not that this circuit is only applied on the way we have already has no applications. So those are there are very many applications, very many areas you can apply. So when you're writing this circuit, you only need to modify a few things so that it suits the application you want to apply it on. So let's just, I want to show you the code and we try to run it. And of course, I've said when you want to write, I have the build.sh, which automates how you run it. And for you, before you use build.sh, you have to make it executable. So for you to make it executable, you're using this command in your terminal. When you run it, the build.sh becomes executable. I've already written that build.sh, but you can always write it in a way that it performs more than it's performing currently. Want to give it more duties, and so you can write it, can also modify it, just modify it. Okay, so for you to run build.sh, you first of all cd get into circuits. That is how I've written this code. Otherwise, you can always change the structure. But my structure is that I have circuits. So you must get inside circuits first before you run it. And then install JS dependencies. To install those, you just cd yarn JS, and then in your terminal, you run yarn. So that command would install the dependencies you want. You want to generate a proof. To generate a proof, we shall use cd.js, then you use yarn generate proof. This generates a proof. We are using bb.js to generate a proof. So you can now verify the proof, get out of yarn, Node.js, and cd contract. Then use forge test optimize. Optimizer runs and so on. So this command is used to verify your proof. So we've generated and verified the proof. That is one way. You can generate it using bb.js and then verify using forge tests. The other way is that you can also prove it. You can also generate the proof using kekak hash, using this command. And before you do that, you must do cd witness, no, cd circuits, then now go execute, so that you have a witness, generate a witness when you do now go execute. And so once you get a witness, You can now generate the proof. Using BB, proof, and so on. Then after generating that proof again, you go further and verify it using the same command we used above, and you have to get back to contract. So let me just share my code, therefore, so that we can do all this mentioned. But you can always write this code and modify it in a way that does more functions. Now, so we're looking at the set membership. The one for set membership is this. So I said we shall get inside circuits. Then inside that you have SRC. Then this is our code main. That is you don't need to click all those, but I just wanted to show you how it looks like before we begin running and it's up to generation of the proof. So this is it. This is these are tests now. At the bottom, we have tests. You can see the test that is supposed to fail. That means the values we've input, none of them matches the value, your secret value. So such is supposed to fail because it means because you wanted to prove, you know, a secret code of a country that is in the list or in the set. The one you provided is not in the set, so the proof has to fail. So let's CD. Let us CD set membership rules. Oh, so my project begins from here. ZK proof patterns in Noir. We begin by that. So we get inside that before we get inside sub branches. So we are there. Then what we want to try is the set membership. So again, CD. Okay, now we are ready to go inside circuits and run it. Nago compile. That's done properly. So we also have Nago over. So because we have it, we can do Nago execute. Otherwise, without it, you cannot. It will bring an error when you do Nago execute without Nago. No, the prove atomil. Without the prove atomil, you cannot do this. Try it and it brings an error. We also have tests in our main. We have tests in our main. So you can do Nago test. Without test, you cannot do Nago test. And you can see our tests were 3, and both of them have passed. So you can see, okay. So if you can see this one is supposed to fail. But the way I've written it, I don't want it to fail. That's why I've written it like this. If I remove should fail, if I remove it and do Nago test, you can see one test has failed, two have passed, and the one that has failed is here. It says, test secret country not in the set. This is that function. This is that function, secret country not in the set is the one that has failed. So it failed because our secret country was code was 77, and 77 is not a member of this set, so it should then fail. So if I return that and run it, it passes. Now, so we've just done Nago compile, Nago execute, and Nago test. The other thing we can do is build.sh, run build.sh, and say that this one you can modify it to perform more roles than what it's currently doing. What it's doing for me, it's doing Nago compile. So if I forget to do Nago compile, this one will still do it. So circuit compilation failed to tell me. If at all my circuit is not well written, it would fail. And when you do Nago compile and the circuit is not well written, it must fail. The other role that is supposed to be doing for me is to generate verification key. And it will be using BB write verification key. And where is it writing it? It's writing it in target and is calling it membership, set membership proof.json. That is where it's, let's just check our target. Our target is here. Let me delete it first of all, because I can see it as things that I ran a long time ago. So if I do Nago, no, it's /build.sh compiles, generating verification key as we expected. Scheme is ultra honk. Finalized circuit size is 36. Verification key saved on target and is called BK. Then it also generates solidity contract. Okay. So let's come to the target and first of all see. It had said it generates verification key. And then it calls it BK. This our verification key has been stored inside target as we expected. The other thing that it has done, it has generated solidity verifier and it has stored it inside contract and has called it verifier.sol. Verifier.sol. So just come inside contract, and inside contract, you will see something here called verifier.sol. So that is what our build.sh did. We can delete it and see whether it's true. Just delete and see whether it's the one bringing it. So we have deleted. Just minimize that, come to contract, and you can see there is no verifier.sol. So let's again run it and see whether it's it that generated that. And you can see the verifier.sol is present, our solidity verifier. Okay. Now, so that is one other thing we can do. We can also get inside, what's our JS. So let's get out of circuits. And get inside JS. And we said we can generate a proof file here using yarn generate proof. And you can see it says the proof has been generated successfully. It has not told us where the proof is, but this is where it is. You can see this where the proof is. So if you want, you can cut this and see it. That is where it is. Now, so the proof has been generated. Our next target is to verify it. So to verify it, the command I gave is here. Just want to copy it and then use it. The command is here. But remember, you have to get out of JS and enter contracts. Cd contracts. Then run that command. And the proof has been verified. And of course, it gives us some things here. You may want to know what they mean later. You have deployment cost, you have deployment size, and so on. And the same thing here. So this is verifier.sol, verifier Honka, verifier contracts, and so on. So we've generated the proof using bb.js and then verified. So we can also generate a proof in another way. I had shown you two ways of generating a proof. So the other way is we have to get out of contract. Okay, so we are out of contract. Let's get inside circuits again and do nago execute to generate witness. After nago execute, we want to go straight and generate the proof because we now have the witness and the command for the proof generation is here. The proof has been generated and it's just inside here again. It should be the same thing. The same thing. And then from there, we get out of circuits and get inside contract as we did before. CD, then CD contracts. Then once you get inside contracts, you can now verify the proof. And the same thing we had earlier is what we have now. And so on. So the proof has been verified. We generated the proof and verified it. Now, so the contents of this Cyprian verified.app.sol, you can see them This example is on my GitHub, Cyprian Sakwa, GitHub. My username is Cyprian Sakwa. So you can find the details here. These are details, and just you may edit and so on. We have the verified solve. This one is generated by running build.sh. You don't need to copy it. It'll be the same thing when you generate using build.sh for the same circuit, to be the same thing. For different circuits, it'll be different. The other thing that you may want to check is when you come here at test, we have starter.t.sol. This one again, you'll have to check and maybe try to write in your own words. There are only those ones. Those are the only thing you may want to check when you go to my GitHub. You can always find them. Oh, there's another one here, the generate proof. When we did yarn generate proof, this is what helped us get the proof. This is a generate proof.ts. And you also have this ts config.json. So these two, you also need to check them and see what content they have and use them to generate proof using yarn generate proof. Without this, then yarn generate proof would not work. Okay, so for the first circuit, we've seen what to do. So we've seen how to write a circuit for set membership and used it to generate a proof. What I said is we can generalize this and or we can customize it to do various functions for us. We can use it to do so many work. So it's not only what we've done. What we've done, we've been using it to identify, to show that we have knowledge of a country that is in the list, but you can use it to do something else. You can use it to verify a vote to be valid, and so on. So now we want to look at another application of zero knowledge proofs or another type of circuit, and this is for graph 3 coloring. Now this is a very important zero knowledge proof circuit because it has applications again in very many areas. One of the areas would be scheduling, others would be puzzles and so on. So the graph 3 coloring, what it does is that you want to have 3 colors and you want to use these 3 colors to color all the regions on the map without having 2 regions that have the same color following each other. So we will not have the same color following adjacent to each other. So what that means in simple terms is that if this is my region and I want to color it, if this is red, then this should be another color. Let me call it even yellow. And so this should be another color, maybe blue. So maybe this would be red again. So if this is red, you cannot put yellow here because to be adjacent to this, and you cannot put red here because we're adjacent to that. Maybe now we can put blue here, and so on. So if blue is here, what about here? You see, you cannot put blue here because we're adjacent. You cannot put red here, blue here because we're adjacent to this. This was blue. You see, you cannot put yellow here. You cannot put red here. That means The way it began is not correct. There's a way then you would identify which color goes where, which color goes there, where, so that the same color does not follow itself. So that is what the three coloring talks about, graph coloring problem. It's not an easy problem. Okay. So the motivation for this is that many zero knowledge and many real world problems are represented as graphs that need proper coloring. And the example of these are scheduling. We want to prove that the schedule is, okay, the scheduling you want to schedule so that two common events are not following each other, so on. So that copies from this three coloring problem. When you're scheduling your events so that they don't follow each other in some, if they are related, or even puzzles and so on. So the other motivation is zero knowledge proofs would allow, or it's not even a motivation. What I'm saying is that what I've just said in point one is that zero knowledge proofs can allow us to do this, can allow us to do the scheduling, can allow us to do the coloring without revealing the coloring itself. Even the scheduling, zero knowledge proofs will allow us to do scheduling without revealing the schedule itself. The areas we can apply these are many. One of them is privacy preserving games, cryptography, anonymous credentials, and so on. Now, so what is the goal of this three coloring problem? The goal is you are to color the nodes of a graph using only three colors so that no adjacent nodes share the same color. That is what we are expected to do. And you want to prove you know such coloring, but keep the coloring secret. You want to reveal that, you want to prove that you know the coloring, which can color nodes. You know the coloring of nodes of a graph using three colors so that no adjacent nodes share the same color. You want to prove you know that. But you don't want somebody to know what that coloring is. So that is what we are doing here. So Noah would assist us to do this and produce a ZK proof as we did in our previous example. Noah would assist us to do this. So the inputs, the fields, stock of 5, secret arrays of colors for 5 nodes, and our colors we shall have 0, 1, and 2, shall number them 0, 1, 2. And then edges will be 6. So what will be, shall we be checking? We check that each node's color is either 0, 1, or 2. So each node we should have either 0, 1, or 2. Those ones are our colors. And remember that 1 can never follow 1, or will not be adjacent to 1, 2 will not be adjacent to 2, and 0 will not be adjacent to 0. So no common colors, no same color follows each other. For every edge, the two endpoints must have different colors. What will be the circuit logic? Color validity. Check that each color is 0, 1, or 2. Edge constraint. Ensure endpoints of each edge have different colors. And then lastly, convert from field to U32 for safe access. Okay. What features are we using? The field type of arithmetic, array, indexing, and for flow loops, assert for constraints, test annotation. So we'll be seeing all this in our code when we begin writing. So the field must be there. Array indexing for loops should be there. Assert must be there. Then test annotation, where we're using how we write the test, if it has to fail and if it has to pass. It must be there because we have to test. Now, so what you'll be doing is you want to reproduce this code and learn. You just copy and paste. This is the helper function. And then we have the main function. This is the entry point. This is where everything is happening. For I between 0 and 5, that means 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Assert is valid color. Then for J between 0 and 6, let mu be the inputs and V be the inputs. Okay, one is U, J, and this other one is BJ. An example of such would be the pentagon graph. We mentioned about it last time in one of our classes. This one has 5 nodes and 6 edges. And then our color is that you can see 0, 1, 2, 0, 1, so that no number follows itself. Then you may want to test for the valid coloring. This is valid because you can see. Let me see. Let me just. Let's even begin with the coloring. That's what you have. And no number follows itself. Even for the edges, U, edges underscore U, and edges underscore B. No color follows itself. So that means this is a valid test. Now look what this one. this 3 is not part of what our colors were to be. Our colors were to be either 0, 1, or 2. 3 is foreign here. So it's what is causing this test to fail. So this test is expected to fail because of 3. So we don't even need to look at these others because this is already a different color from what we began with. Now, why is this one supposed to fail? This one is expected to fail because you can see a color following itself. If this was red, then this would be red. So because of that, this one fails. I don't need to proceed and check here. I've already seen that our colors are following each other. One is following itself. And this also is supposed to fail. In this case, these are our edges. And our edges were to be 0 to 5. That means 0, 1, 2, 3, 4. But you can see 5 is there and is not part of them. Because when you talk of 0 to 5, it means that 0 and 4 included, but 5 is not. Now, so you can add as many tests as you can to test various even boundary points, negatives, and so on. So tests are just meant to prove that your main is functioning as supposed to. So you can put as many tests as you can. I've only highlighted 2 here. But when you're writing a circuit, ensure you put as many tests as you can just to be sure that your main is working as expected. You have to define your secret coloring and the public graph edges, and then generate a proof of your coloring. Then generate a proof that is that your coloring is valid. So you just want to prove that your coloring is valid. Generate a proof for that. Then the verifier would check the proof using the public graph. I can share my code so that, and of course, as I said, is my GitHub. So when you get it time, or let's go to my GitHub and get it from there. So in our previous example, we looked at the set membership. At this time, we're looking at the Noir 3 colorable graph. So what I need to do is I need to get out of the previous example. It is, now we've already gotten out of it. So I want to get inside our next example, which is Noah 3 colorable. So I just want to copy it. I want to copy the name of our next example and CD into it. Okay. There we are. So let me see what folders it has. It has circuits. So let's get inside circuits. CD circuits. Just before that, Let's see what is there so that you're sure that whatever I'm using is the correct thing. So this is what I had shared in the notes. We are coloring, and this is just the same thing we had shared in our PDF. Okay, then there are tests there. How many are these? I had shared only 2. My tests are here. 1, 2, 3, 4. Put as many tests as possible, but ensure that every test is testing one different thing so that you don't have several tests testing the same thing. For instance, you can see when you look at mine, they're not testing the same thing. Like this one is valid 3 colorings, so where the colors do not follow each other. No, they do not follow themselves. The same color do not follow themselves. But look at the next example. I've tested where you've been put in valid color. So you began with 0, 1, 2, but you brought in a different color that was not part of what you wanted to work with. So this must fail. So you look at that. There's a different scenario I've tested. The first one, I tested when you are using valid colors. And now you are bringing in an invalid color. Tested that. And this time, I'm testing colors that are following the same color following itself. Same color following itself. So I've tested that, and again, it has to fail. Then the next one, I've come and tested the edges, and 5 is not part of the edges. Because our edges were to move from 0 to 5, that means 5 is not one of them. Edges would just be 0, 1, 2, 3, 4. So you can see how I did my tests, but I'm not saying that this is the final list. You can test as many scenarios as you can, just to be sure that your main function is working as expected. Now, so that said, we can now see whether it's compiling properly. Now go compile. That is okay. We have our prototype, otherwise would have created one. Since we have it, we can run our execute without any problems. So we can still run our, my previous example, I already showed you how you're supposed to write negative tests. Those that are expected to fail is a way you write them, and I've already shown you that. This is just a commit to your GitHub, what you want ignored. Okay. So having done all those, we now want to do, I don't know, yes, we have build.sh. So let's again do it. Build.sh. Yes, they're doing the same roles as it did in my previous example. The only difference is that we are doing it in a different circuit. It's doing the same role. You can see it has done Nago compile, has generated verification key, and you can find it inside target. You can find it inside target. It has also generated solidity verifier, and you can find it as verified sol inside the contracts. Verifier.sol inside the contract. So you can find it there. Now, so having done that, we can now get inside our JS. So get outside circuits, enter JS, and you want to see whether we can generate a proof by yarn generate proof. Yarn generate proof. Oh, I wrote yarn generate. Supposed to be yarn generate. Yarn generate proof. What is it? No, I did not. I forgot a hyphen. Yarn generate hyphen proof. That's what I was forgetting. Yes, so it has been generated. You can see proof generated successfully. Proof generated successfully. Let me move it here so that you can see properly. Yarn generate hyphen proof. After that, we may want to just verify the proof. So I'm looking at the command, and that command seems I did not update my readme here. Can get it from here. It's the same command. It's just the same command we are using. Since it's not here, let me close this. I can get it from get used to it in this other example of set membership, and it's this one. I did not want to write it. It's a long thing. We have to get outside JS, then get inside contract before we use it. So that proof has been verified. And you can see some details like the ones we had earlier. The proof has been verified. Once that is done, we've just generated a proof by bb.js. So we may want also to generate it using CL. So let's first of all get inside circuit. And generate a witness. Generate a witness. And generate a witness, we want to, so we'll only make a few changes on this. While there is a set membership proofs, will replace by Noir 3 colorable graph. So let me just confirm from Nagotomil if what I'm saying is what is there, because if it's different, then it will not run. Nagotomil, yes, it has it. Nagotomil has no, because Nagotomil is the one giving us a witness. The name of the witness coming from there. So when you write the different witness, it will be looking for a different witness, and you're giving it a different name, so it will not work. So that was that. Just making a few changes on this command. It looks like at the wrong place. It's here. The README is here, the one that has my commands. So I just want to change. So because, okay, so I just want to change this part. But if this is the same, this is what you're looking for. This is the correct one. This is the correct one. It has no 3 colorable graph. So we get outside. No, this one we still use it. Still use circuit. It has been set circuits. Generate a proof. A proof has been generated. And then now to verify it, as we've done before, get outside circuits. Get outside circuits. Then CD contracts. Then after that, you can now verify that the proof is okay. And we get the same thing we got earlier. See here. So that's how we do it. That's how. So what we've been doing, we've written the circuit. We've generated a witness, generated a verification key, a proof, and then verified the proof. And we've done that in 2 ways. We've done proof generation in 2 ways. Now, so what are the applications of these graph 3 coloring problem? One is to prove knowledge of valid graph coloring privately. Another one is zero knowledge games and puzzles. It's used there. And secure cryptographic protocols. That is privacy, for instance, privacy preserving credentials. And you've seen how we've run NAGO tests, test our tests, build.sh, and what it did. And if you don't have yarn, install, you can install by just cd.js and then yarn. Proof generation, we've done it using JS and CLI. 3 Those were two ways of generating proof, and we use them and then verified. Use them and verified. When you're using the CLI, you must first of all do NAGO execute to get a witness, and then use BB prove that this command to generate a proof. Then from there you verify IUCD contract, and then forge test. And this is all used. Even verification is the same. Even when the proof comes from JS, verification is the same. So, what is our summary and takeaway? ZK circuits lets you to prove combinatorial properties like graph coloring. You can do that privately. And that Noir provides a clear language for writing and testing such circuits, and that this approach generalizes to privacy-preserving proofs in cryptography and games. So this is not just classroom work. You can always generalize this to even applications in cryptography and games. And if you require more information, you can always use this link to get documentation and read more on zero knowledge proofs in Noir and many other. Thank you. That is what I wanted us to cover today. So when we meet again, we look at more other advanced lessons in zero knowledge proof using Noir.